All right, so I'm going to be giving sort of a tutorial survey type talk on peeling arguments, including some of the work I've done. So I'd like to start with some of the history of peeling arguments, what they are and what they mean. So one of the earliest peeling type arguments I know has to deal with matchings in a random graph. So it's the standard random graph model. You take some random graph with n vertices and m edges, and then you're going to try and find a large matching. And the peeling way of doing it is to use the following approach, is to just use a standard greedy method. You say, well, I'll find a vertex of degree 1. There's only one thing it can match to, so I'll go ahead and throw it into the matching. Right? I'll go ahead and take that corresponding edge and put it in. When I put that edge into the matching, right, that means that those two vertices are in the matching, so I can take out those vertices and any of the adjacent edges, and I can just repeat this until I run out of vertices of degree 1. Okay, so just because it's early in the morning and it's worth doing a little picture here of, here's a graph, here's an edge with one of the vertices having degree 1, so we peel it out. We find another. Once we peel it out, all of a sudden we have another new vertex of degree 1 that we can peel out and continue. And in this way, we ended up matching all the edges in the graph. Okay. Or getting a matching on all the vertices in the graph. Okay, so this process was one of the early processes studied in random graphs. And what they showed was a sort of interesting threshold behavior. They showed that if the number of edges was sufficiently small, right, that you had a sparse enough graph, then the number of leftover edges would be small. Right. In fact, they show there would be order n, and typically what that means is you can show it goes to 0 with high probability. And they used a sort of analysis looking at this process based on differential equations. And because this is a survey talk, I'm not going to get into a bunch of the details about what these differential equations look like, or even necessarily why differential equations is the right way to model it. This is a standard approach in this sort of process. The way to think of it is you have some sort of Markov chain really corresponding to your random graph. And all you really need to know about your random graph is the state is the degree distribution. And what the differential equations tell you is what the degree distribution in this random graph is going to look like over time. And you can easily write a set of differential equations which explain that to analyze the behavior of the graph as you remove edges using this greedy process. So that's sort of a first example. Let me suggest another example where it comes in satisfiability problems. Okay? So a collection of satisfiability problems that have been well studied are random k-sat problems. So here you have clauses, each of which has k literals, and those clauses are randomly chosen, right? So you randomly select one of the clauses from all clauses with k literals, and you build a conjunction up with some number of those clauses. Okay. So in a typical setting, you're going to have m clauses, n variables, k literal per clause. And there's a very standard, again, sort of greedy algorithm that you can look at here called the pure literal rule, which means that while there's a literal that either it or its negation appears 0 times, you can set its value. Right? That is, if x1 appears in the formula, but not x1 doesn't appear anywhere in the formula, then you might as well set x1 to true. And similarly the other way around. If not x1 appears in the formula, perhaps multiple times, but x1 doesn't appear in the formula, you might as well set it to false. And once you set that value, you can peel away the clauses that variable is in, because you've gone ahead and set those clauses so that they're automatically going to be true. It doesn't matter what the other literals are. And you can continue this process in the search of trying to find a satisfying assignment. So it's the most greedy, typical way you might think of to try and pick out a greedy assignment for a random k-sat problem. And if you like, you can again naturally put this into sort of a random graph. In this case, it might be more natural to think of a bipartite random graph, where you'd have vertices on one side one for each literal, or really each literal pair, and vertices for the clauses on the other. And you'd have, with each vertex, you'd have two counts associated, the count for how often the literal appears and how often the negation appears. And when one of those counts drops to 0, right, that means you can peel away that vertex from the graph, peel away the corresponding clauses and continue. Okay, so this is just to point out that you can also naturally embed this into a graphical process, which is generally a nice way to think about it. And this process was studied by Broder, Fries, and Upval back in 1996. Then I happened to be around at the same place as Andre at the time, and I was able to put these into same sort of fluid limit differential equation framework. And once you do that, you can actually compute sort of the exact thresholds, right? So you can figure out when the number of clauses is sufficiently small, how are you actually going to get to the end? Are you going to complete everything? And if you're above that threshold, then with high probability you're not. You're going to have some stuff left over. And you can actually exactly compute these values based on the differential equations. Okay. So I claim that these two examples are part of really what we should think of as a general approach. And the idea is that I've been seeing this sort of argument appear in all sorts of different places in many different ways. And I just want to try and get people to latch on to the idea that this really should be thought of at this point as an approach because it appears in so many different contexts. Okay, and the basic idea is you start with some sort of random graph, and you're going to be peeling away parts of the graph greedily. Okay, so a typical example is you find a node of degree 1, which we've talked about, and you remove the edge and the other adjacent node from the graph. But there are variations, right? It may be that degree 1 isn't really what you're interested in. It may be that you want to say, well, I'll find a node of degree up to 3 and remove it from the graph. Okay? And this process also has been studied a lot in the combinatorial literature. Right? You might hear the term K-core. K-core corresponds to the maximal subgraph of a graph where every vertex has degree at least k. Okay? And what this peeling process does is it leaves you with a K-core. Right? So in particular, if I just keep peeling away vertices of degree 1, what I'm going to be left with at the end is a 2-core. Right? And if I was peeling away nodes of degree up to 2, then I'd be left with a 3-core, and so on. Okay. And again, there's a very general analysis method that works very well on these sorts of problems. And the idea is that if you start with a random graph, you can show that this peeling process leaves you with a random graph, but generally with a different degree distribution. Okay? So you can just keep reducing the graph. You can essentially set up equations telling you what your random graph looks like all the way down, hopefully to the point where it's empty, or to the point where you stop. And then you have potentially some useful information about what the stopping point of your graph looks like. So now a question is that I like to ask when looking at these things, which is why should anyone care? Okay? I mean, these are great graph processes, and if you're interested in the mathematics, you might like it just for the beauty of the mathematics. But I tend to work in algorithms, data structures, and applications for those things. So the question is, what does this give you? And my claim is that there are actually lots of applications, and I'm going to show some applications to codes and hash-based data structures. And the point is that these ideas not only keep popping up in sort of mathematical combinatorial papers, but much more so these days in algorithm and data structure papers. And I think the reason why, trying to explain why this is interesting from this standpoint, okay, is that it corresponds to greedy algorithms, right? It corresponds to simple greedy approaches. And simple greedy approaches tend to be very good, right? They tend to be very efficient. In particular, the algorithms you tend to get that pop out of this tend to be linear or near linear time, right? Because you're doing very simple operations, just like keeping counts for each vertex, finding vertices with low degree, peeling and continue. And because of that, right, fitting into, I guess, the theme of this whole enterprise, these sorts of algorithms tend to be very useful for big data applications, right, because they work so efficiently. Okay, so let me try and move us to the more application-oriented by looking at low-density parity check codes. And I'm just briefly going to describe low-density parity check codes, hopefully sufficient so that you can get an idea of how this works. Okay? So low-density parity check codes, I have a message that I'm trying to send. And the message here corresponds to the left-hand side. These may correspond to packets, so packets worth of information that I want to send, say, out over the internet. Okay? And I'm going to encode this by including some redundancy. Okay? And my redundancy, what I'm going to use for my redundancy is I'm going to take the exclusive OR of some small collection of my packets. Okay? So each redundancy packet will be a small collection of some of the packets in my original message. And naturally, as you see, you can represent this as a bipartite graph with the message on one side and the redundancy over on the other side. Okay. All right, so the way low-density parity check codes work is the following. Is that the decoding is done by peeling. Okay? And the way to think of that is let's say I've got my redundancy over here. Let's just take it as a given right now that those have come in. And I've got some of my message packets having arrived, but some of them have gone missing, right? They didn't make it through the network. Okay. And so now I'd like to recover them. Okay. Well, recall that initially this redundancy was A exclusive or B exclusive or F. A and F have arrived, so I can go ahead and take those into account with this packet, exclusive or them back in. And I note that, hey, what I have left here is just this node now corresponds to the original message node, B. Okay. Or in terms of my graph process, once this node comes in, I can remove it from the graph and the associated edges. Right? Those dashed edges are things that have disappeared. The dark edges are the things that are still existing. And look, over here I have a node of degree 1. So I can peel it off. I can figure out what this value is, exclusive OR it back over onto the other side. Okay. And I've recovered one of the values that was missing. Moreover, what you can see now is that at the next step, I'm going to continue with another node of degree 1 that will allow me to recover another. If you're looking ahead far enough, you probably see that at that point I'm actually going to get stuck. All right, so peeling arguments have been used in this low-density parity check code setting. And what successful decoding means here corresponds essentially to erasing the entire bipartite graph. How do we end up removing everything, which means recovering everything from the left-hand side? Or equivalently, in the language we've talked about combinatorially, the graph has an empty 2-core. And using the sort of peeling analysis based on differential equations that I'd mentioned, or a different type of analysis based on and/or trees, you can actually find these thresholds. So you can determine the behavior of these sorts of codes very precisely using these sorts of analyses. Okay. Let me give now another application, and this will be the one part of the talk where I'm actually going to go ahead and give a small proof for tabulation hashing. So tabulation hashing is actually an old idea that is sort of becoming new again. And it's becoming new again because of some really great work recently by Mihai Petrascu and Mikkel Thorup. I know many of the people here know, but some may not, that Mihai Petrascu recently passed away at the very young age of 29, leaving behind a fantastic body of work. Where it's a great loss that he left us so early. I like to just take a second. I think it's worth remembering him and thinking about him, and then I'll move on. But the resurgence in tabulation hashing is really due to his recent work. All right, so let me continue and explain tabulation hashing. So suppose we want to hash 32-bit strings into a 12-bit string. Okay. So what we're going to do is set up a big table where we're going to have 4 characters of 8 bits. We're going to think of our 32-bit string as 4 characters of 8 bits. And for each character, we'll look up a 12-bit value. Okay. And these values should be taken to be generated randomly in some way. And we're going to get our 12-bit string by XORing these values together. And so the point is that the amount of memory we need to get a hash value using tabulation hashing is going to be very small, just 32 times 12 random bits. Okay, so for example, if this is my 32-bit string, right, it breaks up, hopefully the color is showing up reasonably here, breaks up into 4 characters. Okay. Character 1 is all zeros, so when I look up the all zero string, character 1, the string for character 2, and so on. I take these values, I XOR them all together, right? And that's how I get my hash value for this string. Okay. So the point is that with a reasonably small hash table, or a reasonably small table, you can come up with hash values. Okay. All right, so what are the properties of tabulation hashing? Okay. Well, it turns out that there are, if you look in terms of sort of standard measures of goodness, right, theoreticians talk in terms of k-wise independent hashing, that tabulation hashing doesn't look that good. But if you look at it in another way, in other ways, and this is what the recent work shows, it actually behaves really well. And part of the how you can understand the reason why it works well is through thinking of peeling. Okay? So if we think of the strings being hashed, we can think of peeling as working in the following way. So think of, say, strings on the left and table entries on the right, again, a sort of bipartite graph. And what we want to do is find something on the right of degree 1. That is, we want to find a string in the set that is uniquely mapped to a specific character value position. Okay. And so the point is that if you only have one string, for example, that's using, right, that has these 8 bits in character 4, okay, then that string is being XORed with its own unique random value. Okay. So it's going to look random from the point of view of all the other strings, because it's being XORed with its own unique random value within the table. Okay. So we can say, hey, this string is independent of all the other strings in the set, and now I can peel away that string and continue the process. And the point is that the peeled set you get in this way has completely independent hash values. Okay? Each one is XORed with its very own random table value. Okay, so how can we use this idea? Well, let me give just a short example of how this is used in some of this work. We have the following lemma. Suppose we hash n keys into m bins, okay, where the number of keys is small compared to the number of bins, right? So we have n keys, table of size m, and n is less than m to the 1 minus epsilon. Okay, so let's think of maybe epsilon as being 1/2. So we have a table of size m and say maybe square root of m keys. Okay? And we're going to hash these keys, which consist of C characters, into these bins. And what we can show is that for any constant a, right, the bins get less than, and this is now going to be some constant number of keys with high probability. Okay? So what you get is that sort of nice load balancing type result saying if you hash in this way, you can guarantee that each bucket is only going to contain a constant number of keys with high probability. And I'm not going to get into the details, but they bootstrap this result further to get Chernoff type bounds for tabulation hashing. Okay, so how does this work? Right, I'm going to let t equal 1 plus a over epsilon. So d, remember, d is the bound on the number of things that fall into any bin, is t to the c. Okay, and so the claim is that every set of d elements has a peelable subset of size t. Right? You say, look, if d elements are going to land in a bin, it's going to have a large peelable subset. Okay? And why is that true? Well, this is just a simple use of the pigeonhole principle. There are c characters, right? In our set of strings, one way to think of a bound on the total number of strings we have is to multiply the number of different positions that are actually used for each character. Okay? So some character position has to be hit in at least d to the 1 over c characters. Otherwise, we have fewer than d to the 1 over c to the cth power, where c is the number of character, total strings, total elements. Okay? So we just look at that character, and that character then gives us a peelable subset of size at least t. Okay? And then we can use this to bound the maximum load. If the maximum load is d, says that there's some t element subset in there, there are most n choose t possible t element peelable subsets to worry about, and the probability that they all landed in the same bin is m to the minus t minus 1. Right? The other t minus 1 all have to land in the same bin as the first. Okay? So then you just apply a union bound, gives that the heavily loaded bin occurs with probability at most m to the minus a. And by the way, what I like about this argument is it shows peeling being used in a different way than the other arguments. Right? In the other arguments, we were using peeling to sort of just take a random graph and get it to empty. Okay? And here, they're explicitly not trying to do that. Right? What they're doing is saying, look, if we have a lot of things that fall into a bucket, there must be some large peelable set inside there, and we use that. So one of the things I really like about this proof is it's showing that there are other ways that we can use peelable sets besides just trying to get the graph down to empty. All right, so this ends the sort of past survey part, and now I'm going to talk a bit about some newer stuff. So I'll talk first about some work on invertible Bloom lookup tables by myself and Michael Goodrich. I should point out there's also related work. There's a previous paper by David Epstein and Michael Goodrich introducing a sort of weaker but similar sort of structure. And there's a recent SIGCOMM paper Michael Goodrich, George Varghese, and a couple others are on that sort of use this data structure for some interesting network problems related to some of the things I'll talk about here. Okay, so I got to give this talk at Google a couple weeks ago before giving it here. And there, when I asked the question, who knows what a Bloom filter is, I get a really good response. But for a general audience, that may be less true. So I always like to ask, how many people have heard or seen Bloom filters? Good. I'm always happy to see that. Right, so Bloom filters are a data structure that's used for set membership, and I'm not going to present all the details about them. That's pretty much all you'll need to know here. But they don't allow sort of a more general sort of thing that we might want to do, which is to do key value lookups. There are some extensions to Bloom filters, namely Bloomier filters, that do extend to key value pairs, and that also, it turns out, you can think of in terms of using peeling methods. But they don't allow you to reconstruct the elements of the set. Okay? So we want to be able to do lookups, and we want to be able to reconstruct the entire set. Okay? So what we were looking for here was something that allows us to do reconstruction. And it's this reconstruction that's really important. Right? People who have seen Bloom filters know you can use them for set membership, but once you stick something in a Bloom filter, you've essentially lost what it was. Right? You can't recover what the actual item is. Itself, you just have a test for set membership. Okay. So to think of these invertible Bloom lookup tables, you can think in terms of the following sorts of operations. We want to be able to insert key value pairs, delete key value pairs, return a value for k if one exists and null otherwise, and we're going to allow you return not found with some probability, which will depend on sort of the load you're putting on your data structure. And we'll also have a list entries operation, which is supposed to return back to you all the key value pairs, which will succeed as long as the current load is not too high. Right? So you have to, as part of your design a threshold where you want to be able to recover all the keys if they're under that threshold with high probability. Okay. So let me talk a bit about this listing, why we think it's an important operation or what it's useful for. So you consider data streams where there's a lot of insertions and deletions going on. So if you like networking, you can think of flows going through a router. If you don't like networking, you can just think of someone trying to track through their ID badges the people entering and leaving a building during the course of a day. And the point is we may want a structure that allows a listing not at all times, right, but at off-peak times where the working set size is small. Right? So in terms of people entering and leaving a building, right, you may want something that figures out, hey, are there any people left in the building at the end of the day, and how many are there? Right? You don't necessarily want a list of who's all in the building, during the peak of the day when everyone's in, but you want to see if there are any stragglers so you can find them and get them out of the building. Same sort of thing for flows. It can be useful to find flows that have initiated but seem to have failed to have terminated after some period of time. And you might look at that at a quiet part of the day, 3 a.m., you might see how many flow characters seem to be left over in your other data structures. And now the point is what we want here in this sort of setting is that the data structure for this listing operation, we want it to be proportional to the listing size, not the maximum size. Right? We want the data structure for this to be proportional not to the number of people that are in the building during the day, but how many people we sort of expect to have as stragglers that we'll have to deal with. Okay? Because obviously the number of people in during the day can be much, much larger. Right? It's easy to develop a data structure that does this, right? That does these operations. You could just keep track of everyone on an insert in a very, very big, say, sorted list of IDs and take them out when they leave, right? But if you think of applications like flows through a router, you can immediately tell that that's going to be a very, very bad idea, right? It's going to take a huge amount of memory to do that and potentially more processing than you want to do that too. Okay, so again, the possible applications are the network flow tracking. You want to do it when the network load is low. And the point is that if you're at a spiked place in the network traffic, you can wait and do it later. And you may also want to be able to do flow lookups at the same time with small failure probability. There's a really fun application to oblivious table selection, but it gets a bit complicated to explain. So I'm just going to pass by it and say if you want to, if you're into oblivious type schemes, there's a fun example in the paper. And another typical application that's going to play into our use of this for coding has to do with database set reconciliation. So you can think the typical setting here is you have multiple devices that are, say, containing your address book or your phone listings or other sort of information, and you want to synchronize them. Okay, and so the point is that you may have a very, very large database, but you expect that the differences, the number of differences between the databases when you sync is going to be small, right? So you'd like to do something where the communication time is proportional to the amount of information you need to sync, not to the total size of the database you have, right? And so IBLTs let you do that. Alice can send Bob an IBLT of her data. Bob goes ahead and deletes his data from the IBLT. And then what the IBLT contains is the set difference, right? The difference between the two IBLTs corresponds to the set difference between these two sets. And if Bob can then pull that out, he can reconcile the two versions of the database. All right, so in trying to analyze IBLTs, it's useful to sort of go in terms of increasing amount of how much trouble your users are trying to cause you. So it's nice to start with a nice system, where you can just assume that each key has at most one value, and people are only going to do pleasant things like delete things they've actually inserted. Okay. But as I've pointed out, in the Alice-Bob scenario, there may certainly be cases where you want to delete things that haven't been inserted, right? So you can imagine less nice systems where keys might have multiple values. Deletions might happen for keys not inserted. Or you could even have extreme cases where key value pairs might be duplicated, and you might want to know how many times has this particular key value pair been entered. Okay. And so we look at a bunch of these scenarios, but I'll focus on the nice system, at least to start, because it's easy to talk about. And the nice system looks like, as people might imagine who've seen these pictures before, like a Bloom filter. We're going to hash each key value pair into cells, right? So the hash, the locations will be based on the key, okay? And what we'll do on an insertion is we can keep a count for each cell, so we can increase the count, and we'll keep a key sum and a value sum. You can think of them as actual sums. Typically, in most cases, you'd implement it, say, with an XOR, okay? So you have something that's the sum of all the keys that's hashed there, the value sum of all the values that have hashed there, and decrease count just as the opposite. Okay? And now on a get, if you're asking me, is there a value associated with this key, what you do is you look up the key, and if the count is 0 anywhere, you return null. Right? That key isn't in the system, can't be in the system because the count associated with that key in one of its cells is 0. Otherwise, if the count is 1 and the key sum equals the key, I can return the value sum, right? So if I get a match on the key, then I assume that I actually have found a place where that key has been hashed to just once, and I can return the value. And otherwise, I can just return I don't know. Okay. And you can do a simple Bloom filter style analysis, and I'm, again, not going to go through it here, but you can figure out things like the probability that you get a not found for a key in the system, and the probability you get a not found for keys not in the system, since somehow that's also a bad answer too. Okay. And now let's move on to listing, which has more to do with the peeling. Okay. So listing, again, this just looks like our typical application of listing. While there's a cell with a count of 1, then I have found a key and a value according to the key sum and value sum of that cell. So I'll output it, and I'll delete that key value from the IBLT so I can continue. So I'm just doing a typical peeling on my data structure, right? So if I have some key and it hashes to these locations and I have a count of 1, I can go ahead and find the key value pair, reduce those counts, and look, hopefully it's given me another location that has a count of 1 that I can use to continue the process. Okay. So again, this corresponds exactly to the same process we've talked about before for finding the 2 core. And so you can use the same sort of analysis that we use for things like low-density parity check codes to actually figure out the thresholds that you can handle for listing. So for 3 hash functions, you get 1.22, 4, 125. These are pretty reasonably small numbers in terms of the number of cells you need in order to be able to do decoding. The more hash functions you use, sort of the better probability of success. Okay. And for those who know the work on low-density parity check codes, it turns out that irregular graphs, that is, using different numbers of degrees, were very useful in that setting. That would correspond to here using different number of hash functions for different keys. You can do that and improve these numbers, but in order to keep it simple, we usually just think of having a constant number of hash functions for each key. Okay. Then you can start playing with this data structure and say, well, what can I do to deal with some of the possible faults, right? So, one possible fault being, or technically maybe not a fault, an extraneous deletion, right? So you delete an item that doesn't have an insert. And now the problem is you have to be really careful because now counts of 1 don't really mean that there's one thing there. Maybe there were 2 keys inserted there and 1 thing deleted there that didn't correspond to an assertion. Okay. So you can deal with this by using an additional check, essentially a checksum, using a checksum on the keys. So if the count is 1 and the hash of the key sum matches its checksum, then you can assume that there's 1 key in the cell and continue. One nice thing is that if you use this approach, then sort of counts of 1 and counts of -1, assuming you're just, say, XORing in values, for instance, are symmetric, right? Everything's completely symmetric. There's nothing, insertions and deletions are now symmetrized operations, and so a count of -1 is just like saying you'd have a count of 1, except the item has been deleted and not inserted. If you want to deal with keys with multiple values, then you need 2 checksums, one for the key sum, one for the value sum. Our standard interpretation is that you have keys with multiple values, that's sort of bad. Our goal is not to return to you multiple values. It's to sort of say, oh, this is a bad state, right, for that key. If one of those values gets deleted, a key can return to a good state later on, of course. So the idea here is that multiple valued keys poison a cell, right? It's just never going to have a count of 1 in the proper sense because there's going to be the same key with 2 values hashed there. And one of the things you can get out of the analysis is that small number of poisoned cells really have a minimal effect. Usually all the other keys, all the unpoisoned keys, can still be listed. And if not, the failure mode tends to be that you have just 1 key that can't be recovered. And in many cases, you can deal with that using some other sort of redundancy. Okay. So now I'm going to move on to a coding application, Biff codes, using these IBLTs for a coding structure. And it shouldn't be really a surprise that you can use these for coding, given the connections with low-density parity check codes I talked about before. Okay. And in fact, the way I like to think of this is really just a fast and simple low-density parity check code variant, where the goal here is to correct errors on Q-array channels for big Q. That is, you can think of packet size objects. Okay? And the reason I think of this as simple is that I'm not going to talk about graphs or matrices or the sort of things we often talk about when looking at codes. I can really express this just in terms of hashing, which is something that I think people feel that they have a better understanding of. It builds on an intrinsic connection between set reconciliation and coding that seems worthy of just more theoretical exploration in general, and on this connection between LDPC codes and these hashing methods by way of peeling. Okay? And again, so I want you to think of, remember the goal here is to really come up with this simple way of looking at low-density parity check codes. Okay? Right, so just remember an IBLT has insert, delete, get list entries, just as we talked about. And this is the basic IBLT framework. It turns out in this setting, because we're using these checksums, right, we don't even really need to keep counts. Right, if you're using checksum, you don't need to see if the count is 1 and then look at the checksum. You can, that's extra redundancy, but really you can just check that the checksum matches. So we're going to not use counts in thinking about this framework. Okay. And again, this is really tied to the set reconciliation problem I talked about. Alice and Bob hold a set of keys with a large overlap and small difference. Again, this sort of possible application of synchronization. You want the parties to learn the set difference, and you want the communication to be proportional to the size of the difference, not to the size of the actual sets. Okay. All right, so what do Biff codes look like? How should we think of them? Okay, so Alice is going to have a message of n big symbols. Okay. And Alice is going to create an IBLT with the keys being ordered pairs of the symbol and the position. Right? We need to get the position information somewhere into the IBLT, so we're going to go ahead and put that in, make that part of the key. Okay. The values for the key are just going to be the checksum that we want. Okay. So Alice's set is just this collection of n pairs. So what Alice sends is Alice sends the message, just sends the values, and for the redundancy, sends along the IBLT. Okay? So Bob receives some bunch of symbols. For right now, let's assume that the IBLT gets through without error, and I'll talk about what to do when this part has errors too in a second. Okay? But Bob receives these pairs, okay? Or Bob receives these values. So Bob, with those values, generates these pairs, deletes them from the IBLT, and then uses the IBLT to perform set reconciliation on the two sets, essentially finding the differences out through the IBLT. Okay? Right, so if there are no errors in the IBLT, Bob deletes the key value pairs. What you're going to be left with is the set difference, which corresponds to the locations where there are symbol errors. Bob lists those out using the IBLT framework and can then find where the errors are and go ahead and correct them. Okay. All right, so the decoding process is just the peeling process. Again, we just look at a cell. If it has one pair in it, the checksums should match with the key, and otherwise it shouldn't match with the key. So the point is you do have to choose a reasonable checksum length so you don't get any false matches throughout the course of the process. Okay? But as long as all your checksums are perfectly fine, then you can do this until all the pairs are recovered and get back everything accurately. Okay. And the process here really looks very much like the IBLT process that we talked about before. Okay? So you can analyze it with differential equations. There is a cost to using this method in that the redundancy, you get sort of an extra factor of 2 over most normal error correcting codes because you're looking at the set difference. You're looking at the errors from both points of view, from Alice and Bob at the same time. So it's an interesting question if we could just get rid of this factor of 2. What if you have bad IBLT cells, right? If there are errors in the IBLT cells, then they're bad and can't be used for recovery. And this just falls into the case that we mentioned before, that it's hard for a key value pair to have all of its cells go bad. It happens with a fairly low probability. So the case that you see when you see an error because of this is that you get one unrecovered value. You can protect that with some sort of simple higher level code on top of your message to begin with. Right? So add some additional error correcting in the original message. Okay. And this is what the code looks like. I imagine I'm close to the end on time. 5 minutes? Okay. Right, so again, the point of this is that it's very simple, very fast code. It's really just encoding is just XORing things together, and decoding is just XORing things together and looking for things where the checksums match so that you can keep on doing the decoding. So let me just suggest some experimental results. I wrote up a sort of a test implementation looking at 1 million 20-bit symbols. I use 20-bit symbols because then also 20 bits describe the location, which is used for the checksum, and then I could do all the arithmetic in 64 bits. And I'm a lazy programmer and didn't want to think about doing things with larger number of bits. So I was looking at 1 million symbols, IBLTs of 30,000 cells, allowing for 10,000 symbol errors and also further errors themselves within the IBLT. Since IBLTs are, since the cells in an IBLT are, at least twice as big as the normal symbol size, I made it a 2% error rate. If you're using big packets, so that the location information is small compared to the size of the packet, it really would be close to a 2% rate. And then I actually chose the parameters to sort of test things out that we would get a noticeable failure rate. Okay, so so the errors that we saw ranged for IBLT cells because one of your items would hash to all damaged IBLT cells. This happens with low probability. Same thing with 5 hash functions. So these are the predicted numbers that you can calculate out about how often you expect this to happen. And over 1,000 trials, we got pretty much the right number of failures, and over 5 hash functions, we also got essentially the right number of failures, which are 0. And as I pointed out, when failures occur, it's just one unrecovered element. So you could protect that with just another simple XOR of all your data to begin with. So the experiments very nicely match analysis. And they're really, really fast, right? It's a fraction of a second to do encoding and decoding at this. And in fact, most of the time that you actually spend is just putting things into and out of the hash table, right? The actual amount of work that you do peeling that you do for real decoding is actually about an order of magnitude less than the amount of work that you do just putting everything into the table to begin with. And this is good because it means, well, first of all, my code's certainly not highly optimized. I'm sure you could optimize that process. One way is you could parallelize, you could certainly parallelize entering items into the table to begin with. Okay, so again, the goal here for Biffed Codes was to design something that was extremely simple. This is like the simplest version of LDPC codes for symbol level errors that I know of. At the expense of some cost and overhead. It's not the most space efficient, right? You can come up with LDPC codes that are better in terms of space, but this is very simple and very fast. So the hope is that it will prove useful for various large data scenarios, and also that it will in itself have didactic value. I suggest that if someone wants to teach low-density parity check codes to a sort of more general audience, teaching it by way of hashing, as opposed to thinking of it in terms of random graphs or random matrices, may be an easier approach or an easier way of introducing it to students. All right, and to conclude the general theme of the talk, right, peeling method, I claim, is going to be is a very useful method, for analyzing bunches of random graph processes. And the point is that lots of processes can actually be put in this framework. We see it popping up all over the place for codes, hash tables, Bloom filter-like structures. So really, we should be thinking sort of the other way around, as theorists often do. We have this nice tool, this peeling. Maybe what we should be doing is thinking in those terms, saying, now that we understand peeling as this useful tool, can we design processes to make use of it? Can we design algorithms and data structures with peeling in mind from the start? And again, the main goal of this is because peeling arguments correspond to very natural, simple, greedy algorithms, you get very simple, time-efficient structures. You may pay, depending on how you set it up, a little in terms of space, but you can usually trade that off against the simplicity and time. So a real question is, what else can we put in this framework? What more can we do with this sort of setup? Which again, I think is going to be found sort of as a core idea in a lot of big data type applications. That's it.
Thank you very much, Michael.
The question is, what happens if you don't know how many errors you're going to have, say in the coding scenario, or how many things you're going to want to list in the listing scenario? So I'd really recommend reading the recent SIGCOMM paper that I mentioned, George Varghese and Mike Goodrich. So that paper sort of combines, they take this structure and they take sort of another sampling method. They're looking at it in a network setting. They use another sort of sampling method so that you can essentially gauge what the right size is on the fly. Right, so they've looked at that question and come up with an additional structure, and sort of by combining these two together, they're able to do some really interesting things in terms of set reconciliation on the fly over the network. So shout out to them.